This is our last topic. Congratulations, you've made it to the end of calculus. We are continuing with the washer method. However, we are now going to revolve around other axes. So we have the x-axis, we have the y-axis. We can make other horizontal and vertical lines our axis. I personally think this is probably the coolest topic because it makes the coolest looking 3D shapes. So let's take a look at these two parabolas. We have y equals 1 minus x squared. That is the above part of the graph, and the below part of the graph is x squared minus 1. What is the volume of the solid generated when the region R is revolved around the horizontal line y equals 3? So last couple topics, we've been revolving around x and y axes. So for example, if I just had this top part of the parabola and I rotated it around the x-axis, it would form this ball 3D shape, and it would look something like this 2D. Now I'm going to revolve around the horizontal line y equals 3. And so if you can imagine taking this from your paper, bringing it up kind of like a slinky, but then it goes through my desk and connects around on the other side. So I end up with something that goes through my words up here at the top, like this. So I hope you can visualize what that looks like. It is donut shaped. And so I have a photo of what it kind of looks like. This isn't exactly it because this one is more circular, but this is actually something in topology called a torus. So you have this donut shape here. Obviously our donut is not quite this circular like I said, but we take this and we rotate it around the line y equals 3. We end up with this donut type shape. So in order to figure out what our radius is here, let's just visualize the line y equals 3 and the bottom parabola x squared minus 1. If I just wanted to find the area of this, so in other words, what I would have here is I would extend this parabola here, and I'm ignoring this top parabola for now. I would have a vertical slice. The top part of my slice would be 3, the bottom part would be x squared minus 1. So as we've learned in previous topics, we would take 3 minus x squared minus 1. So we would have 4 minus x squared. However, I don't want all this area. I want this area that's been cut off by this top parabola. So if I were to draw in the top parabola here, what I actually have is this. So I don't want that full slice. I only want the slice up to here. So one way to help us find that would be to find this area, this slice, or I guess, yeah, area of this slice, and subtract the longer slice away from this little slice, because then I would just be left with this bluish greenish area. So let's find the area of this slice. The top part is 3, the bottom part would be 1 minus x squared, so again this is the top parabola now. So in order to find the difference between the two, so I'm just left with this bluish greenish piece, I would take this radius, the longer radius, and I would subtract away this radius. So it turns out we are going to use the same formula, outside radius minus inside radius. However, my radii will change. Each of the radius will be different. I now have to take into account which axes I'm rotating around. So whatever line you're rotating around should show up in your equation. So my slices are vertical. I am rotating around a horizontal line, so I do need to have the x values as my boundary. So -1 to 1. Now I'm going to go ahead and follow this formula. The outside radius is 4 minus x squared, this piece over here, and I'm going to square that. and then I'm going to subtract away my inside radius. So my inside radius would be 3 minus, parenthesis, 1 minus x squared. Make sure to distribute that negative. So then we end up with 2 plus x squared. So that becomes my inside radius. Just to make sure you fully understand how we got each of these radii, we want just this blue-green area. So when I draw a longer radius here, I have 3 minus x squared minus 1, and I had to distribute that negative. And then for the, just to get the blue-green area, I needed to subtract away this white area here, the part I did not shade in. If I subtract that away, then I'm just left with this. And so that is 3 minus, parenthesis, 1 minus x squared. Okay, if you were to multiply 4 minus x squared times itself using the box, you would get 16 minus 8x squared plus x to the fourth. If you were to multiply 2 plus x squared times itself using the box, and then you distribute through a negative, you would get minus 4x squared minus x to the fourth. Now, if we go ahead and combine like terms, we are just left with a 12 minus 12x squared. That looks a lot easier to integrate. And so the antiderivative would be 12x minus 4x cubed from negative 1 to 1. And so if you plug in the 1 and you plug in the negative 1 and make sure to distribute the negative when you plug in the negative 1, you get 12 minus 4 plus 12 minus 4, which will leave you with 16 pi. And that is the volume of this donut type shape when I rotate around y equals 3. Next example is actually more donut shaped. We are going to take the circular region, x squared equals 1. So this is a circle centered at the origin with radius 1. And I want to revolve it around y equals 3. So again, if you imagine kind of like a slinky, this would come out of the page, rotate around y equals 3. It would go back through the page, come up on the other side. So your donut would be something like this. Okay, so to help us, we need to find this slice right here in the circle. However, last time what we did is we found the larger slice here and we subtracted away the smaller slice. We're going to need to do the same thing here. Take a larger slice and subtract away the smaller slice. So to kind of combine those two together, the larger slice, this bottom piece, this would be 3 minus, and then whatever is the bottom part of the circle. So to help, recall that when you have a circle and you solve for y, you have y equals plus or minus the square root of 1 minus x squared. So the bottom part of the circle would be negative square root of 1 minus x squared. The top part of the circle would be the positive piece of it. So I would subtract away the negative piece in order to get that bottom part. And then in order to get this top part, I would take 3 and I would subtract away the top part of the circle, which is the positive 1 minus x squared. So here, this would be my outside radius. And this top part will create my inside radius. So we will start with the formula again. We need to go from x value to x value. So here, donut is going from negative 1 to 1. The circle is going from negative 1 to 1. And we have 3 plus square root of 1 minus x squared squared. so that's my outside radius, just following the formula, minus my inside radius, 1 minus x squared. Okay, so I will spare you the details of multiplying this out, again using the box. You have to be careful with your square roots. Multiply this out using the box, careful with your square roots. And then once you're done multiplying this, distribute through a negative. And then once you do all that, you go ahead and combine like terms. And it turns out you end up with 12 square root of 1 minus x squared. If you want to practice your algebra, go ahead and pause the video here. Go ahead, practice multiplying this out. Practice multiplying this out, distribute the negative, and combine like terms. You should end up with this. You'll notice this one was a multiple choice question that was not calculator active, and it does actually tell you a certain integral value. And so you can see here that if I bring out the 12, this piece right here is exactly what information they gave me in the problem. So 12 pi times pi over 2. You end up with 6 pi squared. That is the volume of that donut. Okay, our last example, we're now going to rotate around a vertical line. So we have a sine graph and we have x squared. So I hope you can recognize the bottom part is the x squared graph and the top part is the sine graph. Recognize that just by their shapes. You'll notice this one is calculator active. The answers are all decimals. Now imagine the vertical line, x equals 2 here. Again, taking this odd shape, rotating it around this line so that it ends up over here, something like this. Goes through my desk, around the other side, ends up there. So I have a visualization for you that I found online. It would look something like this. There you go. So I have this strange shape here. I would rotate it around a vertical line, so it would end up looking something like this if you imagine this almost like a ring, but all the way up and down this curve. So it looks something like this. All right, let's go ahead and draw our slice. This time our slice has to be horizontal. We are rotating around a vertical graph. So if you were to slice this 3D image, our slices would all be horizontal. So let's go ahead and draw out this slice. Similar to last time, we would take this long radius and subtract away this inside radius. So that's how we would get the outside radius, the inside radius. So now my outside radius is 2 minus this sine curve. However, remember we are needing to solve for x because we're finding the integral with respect to y. Take the arc sine of both sides. And then go ahead and move over that 2 and that pi. So x is equal to 2 over pi arc sine y. The other curve is a little more straightforward. If you take the square root of both sides, we found x. Usually when you take the square root, you need to consider the positive and the negative piece. However, this time you'll see we are in the first quadrant, so I'm only looking at positive values. So I don't need to consider the negative part. So let's go back to our radius here. We're wanting to find this longer radius, which will represent this side of my slice, the outside radius. And so I will need to take 2 and subtract away this arc sine piece. And then to find my inside radius, I need to take 2 and subtract away the square root of y. So it'd be 2 minus 2 over pi arc sine y. That's my outside radius here. My inside radius is 2 minus square root of y. And fortunately for us, this is calculator active. I do need to consider my boundaries. So looking here, I would go from 0 to 1. I'm sorry, I pointed at the wrong axes. I am looking at my y-axis. This is all with respect to y. I would go from 0 to 1 on the y-axis. Go ahead and write your outside radius. That needs to be squared. Minus your inside radius. That needs to be squared. Go ahead and put that in big brackets to show that that is my integrand, and I'm integrating with respect to y. If you want a little refresher on how to plug into your graphing calculator. Okay. Pi, math 9, 0 to 1. Okay, so you're going to need multiple parentheses here. You need a bigger parentheses for the outside, and then, oh, I'm sorry, you actually don't need that bigger, the bigger one. The calculator already gives you the bigger one, but you do need a parenthesis to square. 2 minus 2 divided by pi. Arc sine is the same thing as sine inverse x. And then go ahead and close the parenthesis for the x, but then also you need to close the parenthesis here on the expression so you can square it. So just a quick reminder, we found everything with respect to y, but your graphing calculator really only takes stuff with respect to x. So after we found everything with respect to y, it's okay to go ahead and change the variable. Just like u substitution, we plug in a u, we can still take the integral with respect to a u. It doesn't really matter as long as you set it up correctly. All right, 2.836 when you round, that is answer D.